In mathematics, the method of undetermined coefficients is an approach to finding a particular solution to certain inhomogeneous ordinary differential equations and recurrence relations. It is closely related to the annihilator method, but instead of using a particular kind of differential operator in order to find the best possible form of the particular solution, a guess is made as to the appropriate form, which is then tested by differentiating the resulting equation. For complex equations, the annihilator method or variation of parameters is less time-consuming to perform. Undetermined coefficients is not as general a method as variation of parameters, since it only works for differential equations that follow certain forms. Description of the method. Consider a linear non-homogeneous ordinary differential equation of the form, where denotes the ith derivative y, and denotes a function of x. The method consists of finding the general homogeneous solution for the complementary linear homogeneous differential equation and a particular integral of the linear non-homogeneous ordinary differential equation based on. Then the general solution to the linear non-homogeneous ordinary differential equation would be if consists of the sum of two functions, and we say that is the solution based on and the solution based on. Then, using a superposition principle, we can say that the particular integral is typical forms of the particular integral. In order to find the particular integral, we need to guess its form, with some coefficients left as variables to be solved for. This takes the form of the first derivative of complementary function. Below is a table of some typical functions and the solution to guess for them. If a term in the above particular integral for y appears in the homogeneous solution, it is necessary to multiply by a sufficiently large power of x in order to make the solution independent. If the function of x is a sum of terms in the above table, the particular integral can be guessed using a sum of the corresponding terms for y. Examples. Example 1. Find a particular integral of the equation the right side t cos t has the form with n equals 1, alpha equals 0, and beta equals 1. Since alpha plus I beta equals I is a simple root of the characteristic equation, we should try a particular integral of the form substituting yp into the differential equation. We have the identity comparing both sides, we have which has the solution. We then have a particular integral. Example 2. Consider the following linear non-homogeneous differential equation. This is like the first example above, except that the non-homogeneous part. As a result, we have to multiply our guess by a sufficiently large power of x to make it linearly independent. Here our guess becomes, by substituting this function and its derivative into the differential equation, one can solve for a. So, the general solution to this differential equation is thus. Example 3. Find the general solution of the equation. F is a polynomial of degree 2, so we look for a solution using the same form, where plugging this particular integral with constants a, b, and c into the original equation yields where and replacing resulting constants to solve for the general solution, where is the homogeneous solution. Therefore, the general solution is